Okay, let's dive right into this. We all know the difference between hot and cold, right? It's pretty intuitive. But have you ever really stopped to think about what those words actually mean on a fundamental level? Well, today, we're going to pull back the curtain on the incredible invisible physics that's happening in your coffee cup every single morning. This is your essential primer on thermal energy. So it all kicks off with a super simple question, one you've probably experienced 100 times. You pour that perfect hot cup of coffee, you get distracted for a few minutes, and when you come back, it's lukewarm. Or you grab an ice-cold soda from the fridge, and before you know it, it's basically room temperature. So what's the deal? Why does everything always seem to drift towards that, boring middle ground? Well, the answer isn't in the drink itself. It's hidden away in a world that is completely invisible to our eyes. To really get this, we have to shrink ourselves down. We're talking about going microscopic, to a world that controls everything we feel and experience as temperature. So, our journey into that unseen world starts right here. First stop, we need to understand what everything around us, and I mean everything, is actually made of. Once you get this one idea, trust me, everything else just clicks into place. Okay, believe it or not, the chair you're sitting on, the air you're breathing, this very screen you're looking at, it's all just a giant collection of tiny, jittery little particles called molecules. And here's the wild part. They never stop moving. Ever. They are in a constant, chaotic dance 24/7. All right, so everything is made of these dancing molecules. Cool. But what does that have to do with your coffee getting cold? Well, as it turns out, it is the entire reason. This right here is the aha moment. This is the absolute key. Hot isn't some kind of magical property. It's just our word for trillions upon trillions of molecules zipping and vibrating around at incredibly high speeds. And cold, well, that's just what we feel when those same molecules are moving really, really slowly. It is that simple. At its core, temperature is just a measure of how fast molecules are moving. So let's break that down even more. When something is hot, say a flame, what's happening at the molecular level is pure chaos. You've got molecules moving insanely fast, packed with what scientists call high kinetic energy. Now, on the flip side, something cold, like an ice cube, has molecules that are kind of just lazily vibrating in place. They have very low kinetic energy. It's all the same stuff, just moving at totally different speeds. And hey, I just used a sciencey term there, kinetic energy. Don't let it throw you off. It's really just the official name for the energy of motion. That's it. If something's moving, it has kinetic energy. The faster it moves, the more kinetic energy it has. Simple as that. Now here is a really, really important detail. A thermometer isn't measuring the speed of just one singular molecule. That would be impossible. Instead, it's measuring the average speed of all of them put together. You can think of it like cars on a highway. Some are speeding, some are going slow, but the average speed tells you about the overall flow of traffic. Temperature is basically the traffic report for molecules. All right, we've got the basics down. Hot means fast molecules, cold means slow molecules. So what happens when you put them right next to each other? When your hot coffee meets the cool air in the room. This is where the action happens. This is where the energy transfer begins. I want you to picture a microscopic game of pool. The fast-moving molecules in your warm coffee are like the cue ball, flying across the table. When they hit the slower molecules of the colder air, bam! They smash into them, transferring some of their energy. With every single collision, the coffee's molecules slow down a little, and the air's molecules speed up a little. That transfer of energy is what we feel as things cooling down or warming up. And this is one of the most fundamental laws of the entire universe. The energy that left your coffee didn't just vanish into thin air. Nope, it was transferred directly into the molecules of the air around it. The total amount of energy in the system, the coffee plus the air, stays exactly the same. It's just been redistributed. So does this frantic exchange of energy just go on forever? Not at all. Nature actually has an end goal in mind, and that goal is perfect balance. It's a state that scientists call equilibrium. Equilibrium is the final destination. It's that point where the energy has been so evenly shared and passed around that the fast molecules have slowed down and the slow molecules have sped up, and they all just kind of meet in the middle. The big energy exchange calms down because, well, there's no big difference in speed anymore. And that is exactly why your hot coffee and your cold soda both end up at room temperature. They are constantly transferring energy with the air, the table, everything around them until they all reach that balanced state of equilibrium. From our perspective, we just feel this as a single, uniform temperature. That lukewarm cup isn't a failure. It's physics achieving perfect balance. So let's just boil this all down, shall we? If you remember anything, remember these 4 key things. 1. Everything, and I mean everything, is made of constantly moving molecules. 2. Temperature is just our way of measuring their average speed. 3. Energy always, always flows from hot to cold, from the fast movers to the slow movers. And 4. This whole process keeps going until everything hits that balanced state we call equilibrium. And all of that leaves us with one final kind of mind-bending thought. We've just defined cold as slow molecular motion. So what would happen if you could just keep slowing them down and down and down until they stopped moving completely?